in calculus, really. Calculus. We are now going to start what are called limits. You've done a little bit of it last year at this actually very time, because I just did it last week with the pre-calculus class. But before we begin, let me just explain what calculus is, the two fundamentals that we're actually going to talk about this year. Calculus centers around two fundamentals. The first one being, we are going to focus, and that's going to be on this first half of the year, on finding the equation of a line tangent to the graph of a function at a point. Finding the equation of a line tangent to a graph, otherwise known as a tangent problem. We're going to look at a curve, a bunch of curves, and I want to know at this point right here, what is the equation of that line? And you may think to yourself, well, that seems really easy to find. It's not as easy as it sounds. It's actually what all of the Isaac Newton, Leibniz, and Fermat's, they all thought about and had to figure out this point right here. How do I get that equation at that point right there? That's what we're going to focus on this first half of the year. Second part is then finding the area between the graph of a function and the x-axis. Finding the area between. And that's pretty cool. So you'll have this this curve, and you'll be asked to find the exact area under that curve. And again, seems logical. Seems like something that should be so easy to do, but we got problems here because, you know, your knowledge in geometry is limited to like circle equations and square equations. I mean, you don't really get to know like what figure is that right there when you have all these curves. So we need to figure out, calculus will actually help us find the area under a curve. We'll do that again more toward the second half of this year. But let me go back to number one about this, finding the equation of a line tangent. By the way, tangent meaning not to be confused with sine, cosine, tangent. Do you know what tangent means in geometry? It means touching at one point. Finding that one point where the line touches at the line, and that is known as our tangent problem. Because I can easily draw a line, and I can take 2 points on this line, let's say P and Q, and I can draw what's called a secant. Secant is where a line crosses through 2 points, okay? And that's really very easy for us to do. PQ is the secant. But we want to make a tangent line. So what mathematicians long ago were like, okay, well, what if I moved Q a little bit closer and then drew my secant line? Well, if I moved it even closer and then drew my secant line and moved it even closer and closer and closer, okay? As Q is approaching P and I make these beautiful secant lines, I'm eventually going to resemble the tangent line. Wouldn't you agree? If I keep getting closer and closer and closer, as close as I can, don't you think I'll eventually hit that tangent line? So as Q approaches P, the secant line more closely approximates a tangent line. Now, P could never become Q. We can't have that happen because unfortunately, we wouldn't be able to get a slope out of that. There's no way to get a slope. So that's why we have to go as close as we can to P. So close as we really close, as you'll see today. We have to get really close to P in order to get this tangent line problem. That idea of really close is called limit. And you can write that down. The idea of really, this is great, like mathematical definitions. Really. The idea of really close is called limit. Here is the limit definition. It is approaching a value.
It was per.
Without necessarily reaching it. The limit would be approaching without, you don't have to actually hit that limit. The mathematical symbols look like this. The limit as x approaches a of some function is equal to L. Right here, by the way. This is how the limit of your function f of x as x approaches a. And just so you know, the students always get concerned like, well, what are you looking for? You're looking for your output. You're looking for your y values. That's what you want to look at. What are the y values? Are they all going toward the same thing? That's what we're looking for in terms of limit. Okay, so this is what we're going to spend most of our time today doing. We're going to do it with the calculator and graphically. Sorry. Here you go. All right, so homework directions tonight are going to say the following. We got 5 examples to do. Hopefully I can get through them all. I'm not going to get through this whole what I want to do today. We're going to save a little bit for tomorrow. You're going to estimate the limits graphically and with a table of values. We want to know the limit as x approaches 2 of negative 3x plus 1. I need you to see this graphically. And then we're also going to look at it on a calculator table of values, which we did last year. I'll just kind of refresh your memory on that one also. Okay, so what is the limit of the function negative 3x plus 1 as x approaches 2? So let me just graph this for you. You can graph it in your calculator. You can put this into y equals right now. Y equals negative 3x plus 1. But you should all know how to graph this. You go to 1. You go down 3. 1, 2, 3 over 1. Over 1. Or you could go up 3. Okay. So you have this beautiful line right here. And here's what I'm asking you. Here's what I want you to understand what this mathematically is asking you. That as you approach 2 on the x, here's 2, okay? As you get really close to 2 from what's called the left side and the right side, okay? So as I get to 1.9, 1.999, or even 2.01, and I go to the graph, I want to know what my y value is going to be. I want to know what the y's would be, okay? What is that value on the output side going to be?
5.
Most of you could probably see what it's going to be right now. Not 5, what?
Negative 5.
Negative 5. Negative 5, it kind of looks like it could be, right? Let's just double check with a beautiful calculator. This is what we did last year when we learned about continuity. Negative 3x plus 1. If you don't remember, you need to change your table. So you go to second window in the calculator, which is the table setup window. You are going to start your table at wherever the x value is. Where do you want it to start? I want it to start at 2. So you're going to put 2 right there. Your triangle table, this one right here, means the change in the table. I want to be really close to 2. So I'm going to go by 0.01. You could change it to 0.001, but 0.01 is a pretty good value. So my table start will be at 2. my triangle table, the change in my table, I want it to be at 0.01. Then go to second table and go up 2 spots. Do you remember kind of doing this last year when we looked at tables? So you're going to write this down. And by the way, your table of values always helps you. Always, always, always will help us out. But 2 is where we go. We approach it from the left and we approach it from the right. We get as really, really close to 2 as we possibly can. What is our Y value getting close to? Well, let's see. At 1.98, I'm at negative 4.94. Then I'm at negative 4.97. Negative. Did you type it in correctly? Let me look. Come here, Chad, bring it up. What does it look like I'm approaching, guys, from this direction? Negative 5. And again, some of you already saw that. Some of you already figured that out. What did you do to just figure out, well, couldn't we have just done what? Plug it in. What's negative 3 times 2? Plus 1.
Negative 5.
Just said it. All right. So now we're going to do the limit as x approaches 1 of x squared minus 1. Can anybody right now figure out what the limit's going to be?
0. 0.
What'd you do?
You put the 1 in.
1 squared minus 1.
0.
Was it going to be 0? All right, let's just double check. First, I want us to graph this because I really do want to get a picture in your head. There's a reason for there's a method to my madness, y'all.
I can't.
You're crazy. You're crazy.
2 be 3. So here's what I'm asking you for again visually. As I approach 1 from the left and right, what is my Y value turning out to be? And it definitely looks like I'm right there at 0. But we are going to use our table of values to check. So let's again go through this process. In the Y equals, Jed, you're going to type x squared minus 1.
Very funny.
I know. Then you're going to go to your table and you're going to start it at 1. This is your start.
Very funny.
Look at your table, go up 2, and you write this down. 0.98, 0.99, 1, 1.01, 1.02. Tell me, what does the Y values, what does it look like they're approaching? 0. Okay, really hard stuff so far.
Stop there, right? Easy point.
Come on, people.
At the bottom of my page.
Are we Einstein yet?
Are you Einstein yet? No. All right, let's do another one. Come on, Mrs. Seta. What's the limit of this one, guys?
3x or 3
0.
9 minus 9 is 0.
0 over
0.
There is no
One.
undefined.
Okay, so if you plug 3 in right now, what you just said to do before, 3 squared is 9 minus 9 is 0, over 3 minus 3 is also 0. Are we allowed to have 0 on the bottom?
No, undefined.
So a lot of you are going to say undefined. There are times where limits don't exist, which I'm going to show you in a minute. But the limit exists for this one, everybody. Let me show you. Put this in your calculator, everybody, please. And when you put it in, I've got people already doing this wrong in the other classes. You must put parentheses around the top and the bottom. Do that right now, please. If you don't put those parentheses, your calculator is going to divide the wrong thing. So please do that for me.
Yeah, what does the parentheses?
If without those parentheses, it would actually do 9 divided by x minus 3. It wouldn't do the whole entire thing, the calculator. So, all right, just so you see, if you hit graph right now, it looks like a straight line, doesn't it? Looks like a straight line going at 3, 1, 2, 3. Okay. If we go to our table, and again, we do our table of values and we hit 3, is where we're going to start at. Go by ones. And let's look at our table. Go up to, it says error. That is because you all don't see it in the graph, but there is a hole in this graph. There's actually a hole at 3. Holes are okay, actually, when limits. So if I'm looking at my table of values, 2.98, 2.993, 3.01, 3.02, I am approximately approaching what value? Even though it says error, what value? Okay, so let me tell you why. Look at this definition again. The definition for limit, look.
Okay.
Limit is approaching a value without necessarily reaching it. Even though I have an error there, I am approaching a value and I don't have to actually be on that. I can have a hole in my graph. My limit for this function right here is 6.
Oh, whoa.
The limit for that function is 6.
So it's not 0.
It's not 0, and it's not undefined, like a lot of you were saying.
Even though it says error.
Even though it says error, as long as it's approaching,
That's what I was gonna
you're going to be fine, according to limits.
So pretty much on that one, you have to do the calculus.
Exactly. That's why I'm saying the calculator is your best friend.
What if you didn't have a calculator?
You're going to have to do a lot of plugging in and chugging out. All right. My last thing I'm going to talk to you today about is this thing called one-sided limits. Sorry. And no. One-sided limits. And I'm going to give you, again, little math notation here. Don't freak out by it. If you don't understand it, just bear with me. This is the notation for what's called a left-handed limit. It looks like this, the limit as x approaches c, and then they're going to put what looks like a negative. That's not a negative. That right there means from the left. This right here is what we call a left-handed limit, coming from the left.
That's me.
A right-handed limit would be the limit as x approaches c, and then they would put a plus sign. That is a right-handed limit. Does not mean signs, by the way. This does not mean a negative and a positive. It just means from a right and a left, and I'll talk about what that means in a minute. Those are called one-sided limits. Now, the proper definition for the existence of a limit at a point, existence of a limit at a point. And write this down. The existence of a limit at a point. The limit as x approaches c from the left of a function needs to equal the limit as x approaches c from the right of that same function. If the right and the left are the same limit, then the limit as x approaches c of the function is also L. Okay. Now again, this is very calculus-y right here. Just write it down and I will show you what I mean with my next example. You'll be like, okay, here we go. The limit as x approaches c from the left of the function has to equal the limit as x approaches c of the right of the function. Once they both equal the same thing, then you have yourself a limit at that point. Okay, at the point C.
How is that different from what we just did?
Gonna find out. Ready? All right. Example 4. There's actually 3 of the questions in one. We are going to find out the limit as x approaches 0 from the left of the function 2x over x in the absolute values. We're then going to find the limit as x approaches 0 from the right of 2x over x in absolute values. Then we're going to find out the limit as x approaches 0. These are 3 different questions. These will be on your next quiz. You have to understand what I'm about to tell you right now, this idea. I want you to put the absolute value of 2x divided by x in your calculator. If you don't remember how to find the absolute value, it's math num abs. Okay, make sure you all type this in your calculator right now, okay? After you type it in, you are going to go to your table set and you're going to start again where? Where are we starting?
0.
0, right? Okay, so 0, you can go by 0.01, that's fine with me. Go to your table and go up. Now let me explain something to you. This one right here is the limit as I approach 0 from the left. Meaning on your table, look, you're only concerning yourself right there. That is what's called the left. Coming from the left of 0 would be coming from a negative direction, agreed? So this is your table, not the bottom. You would have a table that looks like this. You go from negative 0.02, negative 0.01, 0. And what you have is negative 2, error. What is the limit then on the left? What's the limit? What's it approaching?
0.
Try again, look. Negative 2. My limit on the left is negative 2. All right, then this one is the limit on the right-hand side. So I cover this one right here. Coming from the right means coming from a positive x. So 0.01, 0.02. I've got 2, error. Again, I don't have to actually hit it. I just have to find out what the values are approaching. What am I approaching from this direction? 2. That's the limit on the right. So if I ask you this question, listen to what I'm saying, please. Please, I promise you it's going to be on a test. If I gave you this as a question, you would say, Mrs. Setta, the answer is negative 2. If I gave you this as a question, you would say the answer is 2. Are you with me? But if I gave you this one right here with no little symbol up here, you have to make sure that they both hit the same limit. That's what I just had you write as your definition. Where's my piece of paper? Of course I lost it. That they're both hitting the same limit. Are they both hitting the same limit? We can see right there. So your answer for this one and this one only is, are you ready? DNE, which means does not exist. The limit does not exist. If the right and the left are too different, then the entire existence at that point does not exist. What? Craziness, but that's what it means. Does that make sense to you? Can I go through this again? Because I'm kind of scared. I'm telling you it's on a quiz. This has a limit of negative 2. This one has a limit of 2, the right side. But both of them, do you agree, are both hitting 2 different limits? Then they don't exist. Okay? All right.
If they both hit positive 2, the limit for...
If they both hit, would be 2. Correct. Nice. All right, let's do one more. This is a piecewise, and then we're done. I told you it's a long one. I'm sorry. Too bad Crowbar's not here.
Pennywise.
No.
I love these frogs. So where are you doing that?
All right, so I'm giving you the function. It's a piecewise function, x cubed plus 2 if x is less than 1, and then 2x plus 1 if x is greater than or equal to 1. Find the limit as x approaches 1 for this function. If you don't remember how to type this into your calculator, I'm going to try to refresh you real quick. It's pretty easy, and you would type x cubed plus 2 into your calculator into the y. Oops, I just hit squared. X cubed plus 2. Then, yeah, where you see the if, you hit divide, parenthesis, x. This right here, the symbol is located in second math. Go to less than 1, and then close the parenthesis. So your first line should look like that. X cubed plus 2 divided by parenthesis, x less than 1. close parenthesis. You do the same in y2 now. Hit this one.
Where do we see that?
2x plus 1 divide parenthesis x second math greater than or equal to 1.
Do you say that the symbol is in math or?
Second math. It's in the test function. All right. We are concerning ourselves getting close to the point of 1, so I'm going to change my table to 1. I do want you to see this graph in a minute, but we're going to just look at the table. Okay, don't freak out about all the errors. Remember, it's not about error. We don't even care about error. It's what I'm approaching from that side. Okay? So if I were to make a table of values for this, 1 would be here in the middle. I'm going to go to 0.98, 0.99. What am I approaching at 0.98? I'm approaching 2.94, yes?
Yes.
And then at 0.99, it's 2.97. At 1, even though it says error here, it says 3 there. So I'm going to write 3. What's at 1.01? What's at 1.02? 3.02, 3.04. Am I approaching the same limit from both sides, y'all?
Yeah.
What's that limit?
3.
The answer is 3.
6.
And again, just so you can see the graph, because you are going to have to look at this visually. You have the cubic function, and then you have a straight line. And it looks like in my graph, it looks like in mine, I don't know if you can see it in yours, it looks like there's a hole there. So I would have been like, oh, it does not exist, or there's an error or something. But again, it's not about holes. It's about what are you approaching? You're doing this cubic thing, and then you go line like that. And so right at 1, I actually am hitting 3. I'm getting very close to hitting 3 on both sides. So welcome to calculus. This is limits. This is what calculus is all about.
So we can hit 3.
You can hit 3, yeah.